Okay, now that we've defined what an acid and a base are, we can talk about how they react with one another, and that's sort of the point of this chapter. Remember, we're talking about reactions in aqueous solution, reactions in water-based solutions. So let's discuss how acids and bases react in these water-based solutions, and they do so in what's called a neutralization reaction. And what this means is when an acid and base react with one another, neutralization reaction, I've abbreviated reaction, RXN. When an acid and a base react with one another, the acid neutralizes the basic properties of the base, and simultaneously the base neutralizes the acidic properties of the acid. So I'm just going to write this as a reaction between an acid and a base. So how do I recognize a neutralization reaction? Well, with practice, of course. Knowing my strong acids, my strong bases, my weak acids, my weak bases, sort of recognizing when these protons exist when attached to polyatomic ions is very helpful as well. And being able to recognize the hydroxide ion in various substances is helpful as well. We're going to go ahead and take the simplest neutralization reaction, sort of the standard. We're going to react HCl with sodium hydroxide. And notice the way that I've written this. I've written dissolved hydrochloric acid in this form, even though this isn't what's in solution. We know this is a strong acid, so this actually exists as H+ and chloride ions. Similarly, we know that dissolved sodium hydroxide doesn't exist as sodium and hydroxide stuck together. It exists as dissociated sodium ions and hydroxide ions. You have to know that we do this. We chemists will sometimes write things like this, even though we know in our heads this isn't what's in solution. But what you want to do when you're sort of trying to predict what happens in an acid-base reaction, what you want to do is you want to find the proton in the acid, and you want to combine that with the hydroxide in the base to make water. It's very easy to see. Here's the H+ from the acid, and here's the hydroxide from the base. It's going to make water. What's left? Well, let's see. If this is really H+ and Cl-, and this is really sodium positive and hydroxide negative, and we've used this and this, what we see that's left over is dissolved salt. It's salt water. So we'll just write that over here. NaCl aqueous. Very easy. It's a neutralization reaction. So what you do is you start with an acid. This is the same acid that's in your stomach. It's stomach acid. So you take stomach acid, you react it with this stuff, which is found in oven cleaner. That's pretty nasty. And you end up with salt water. So you can, at least in that colloquial sense, you can see how things that are kind of nasty neutralize each other, and they form material that's more neutral, much less acidic, much less basic, and in fact, these substances, they are neutral. I want to show you another particular neutralization reaction. This one's a little tricky. We're going to react sulfuric acid, which that's got 2 protons, and we're going to react this with magnesium hydroxide. And I'm writing a solid here. I'm writing solid magnesium hydroxide because generally speaking, magnesium hydroxide doesn't dissolve really well. And magnesium hydroxide is found in milk of magnesia. It's the active ingredient. Well, why would I drink this stuff? Well, remember, I just told you that your acid has stomach in it. Your stomach has acid in it, and sometimes that acid gets a little too much. And so when you want to neutralize an acid stomach, you're going to take a base to neutralize it. That's what's going on here if you got an upset stomach sometimes. So what's going to happen here? Well, in this case, I have 2 protons and 2 hydroxides, so I'm probably going to get 2 waters. Let's write that. And just to sort of see how this might happen, this can donate an H plus and an H plus and a single sulfate. And this can donate an Mg2 plus and 2 hydroxides. And I see, okay, that's going to pair with this. This is going to pair with this. And I'm going to end up with dissolved magnesium sulfate. Unfortunately, in this case, this ion and this ion, they balance, so they exist in a 1-to-1 ratio. It could also be the case that I would, for example, let's react stomach acid with it. So I'm going to put HCl plus magnesium hydroxide. What's going to happen here? Here I've got 2 hydroxides that need to be neutralized in the neutralization reaction, but the hydrochloric acid is only donating 1 proton. So how do I neutralize both hydroxides with a single proton? Well, you don't. You're going to need 2 of these. I hope that makes sense. I'm going to use 2 of those. Aha! Well, now I have it, right? Let's see. I've got an H plus. I've got an H plus. And I've got 2 Cl minuses. I've got 2 chloride ions, don't I? Over here, I've got a single magnesium, and I have 2 hydroxides. Ah, well, this pairs with this, making 1 water. This pairs with this, making a 2nd water. So let's draw our 2 waters over here. And what am I left with? It's beautiful. Look at that. I've got a magnesium with a +2 charge, and I have 2 chlorides present to balance that. It should always work that way. So what I'm going to end up with is dissolved magnesium chloride. And notice I've got 2 chlorides, 2 negatively 1 charged chlorides to balance the +2 on the I almost said manganese, +2 on the magnesium. We can write these reactions in terms of complete and net ionic equations, like we've learned about before. Let's do the simple one. We'll do the simple one first. So we got HCl aqueous plus sodium hydroxide aqueous. If I was going to write this as the complete ionic equation, I'm going to break all these into their constituent ions. So I'm going to have H plus aqueous plus chloride aqueous plus sodium aqueous plus hydroxide aqueous, and that's going to go to water. HOH is water, and we're also going to get sodium aqueous plus chloride aqueous. This would be the complete ionic equation for this neutralization reaction. The net ionic equation, you might remember, is that we cross out, we get rid of the spectator ions, which are the ions that appear dissolved on both sides of the equation. So let's see, that's going to be H plus, no, it's not H plus because that gets locked up in water. Chloride, that's aqueous and aqueous. Same thing going in as this is coming out. That's no net change. Sodium ion going in, sodium ion coming out, we can cross that off. Hydroxide ion going in, that goes to water. That changes, so we better leave that alone. So we write what's left. H plus aqueous plus hydroxide aqueous goes to water, which is the basis of a neutralization reaction. Protons and hydroxides go to water. This will always be your net ionic equation for a neutralization reaction. Now you may have 2 of these. You may have 2 waters forming or 3 waters forming, depending on the number of protons in the acid and the number of hydroxides in the base, and you got to pay attention to that. Let's do an experiment here. that illustrates this particular reaction. Sulfuric acid dissolved plus magnesium hydroxide. That's the active ingredient in milk of magnesia. So here's my sulfuric acid that I'm going to be using. And I have some water that I'm going to place the magnesium hydroxide in. Looks very white, doesn't it? Doesn't look like it's dissolving very well into the water. That's why I've written this. That's why I've written the magnesium hydroxide as a solid. Does not dissolve well at all. You see that cloudy mixture? That tells me there are little solid particles in there. We have a heterogeneous mixture of water and undissolved solid particles of magnesium hydroxide. Now what I'm going to add to this mixture is what we call an acid-base indicator. The particular acid-base indicator that I'm going to add will be blue or violet, blue or purple colored in a base, and it'll be red, orange, or yellow in an acid. If it's neutral, it'll be green. So let's see. The only way that this will turn blue or violet is if there are free hydroxide ions in there. That's what a base is, remember? So let me add a little bit of this indicator. You know, I claim that magnesium hydroxide, even though it doesn't dissolve real well, a little bit of it does. Let's see if there's free hydroxide ions in there. Oh, look at that beautiful purple and blue. That purple and blue color tells me that even though most of the magnesium hydroxide is undissolved, there's some of it that has dissolved and has formed free hydroxide ions that are able to interact with this indicator dye, making it, in this case, purple. That's very basic. This is a very basic solution from some of the magnesium hydroxide that's dissolved. Now, I'm going to add some sulfuric acid to the mixture to see if I can neutralize the violet-colored indicator. And of course, what I really want to neutralize is the magnesium hydroxide. So I'm at a single drop of this, just one. I'm going to swirl. Oh my goodness, I saw a whole bunch of colors there. There's a lot going on. And it looked like it went to a blue color, kind of where it leveled off. Oh, maybe it's even going all the way to purple. Something's going on there. Let me add another drop. Let's add 2 drops this time. All right, 2 drops. Red, orange, yellow, green. That went really fast. Looking kind of blue or aqua-ish colored right now. What in the world is going on? It's getting a little darker blue. It's even getting back to violet, isn't it? Sure is. Let's add another 2 drops and swirl. Red, orange, yellow, green. And if we wait, sure enough, it went to blue, and it looks like it's going to violet again. Add some more. I'm going to add a little bit more this time. There we go. See if we can't get it to stay red. Red. Oh my goodness. What in the world is going on there? It's a little bit complicated, but let's talk about it. Let's talk about it a bit. We'll come back to this in a bit. Okay. Here's the chemical reaction that's going on. It is a neutralization reaction. We have to think about what's in the beaker. Oh, it's purple right now as I look at it. So I'm going to sort of draw what's in the beaker. we have a lot of solid magnesium hydroxide that's undissolved. It's spread throughout the mixture, of course, as little tiny particles. But I'm just going to draw it as a big bar of solid magnesium hydroxide here on the bottom. Okay, this is going to represent the solid that's in there. A little bit of this dissolves, just a little bit. So we're gonna just make like 2 hydroxide ions, okay? And of course, for every 2 hydroxide ions that dissolves, we're gonna need a magnesium ion. That's got to happen. You got to keep charge balanced. When I give it a squirt of the acid, I'm putting in a bunch of H2SO4. So let's just say, okay. Well, there's two protons for every sulfate. So if I squirt 1 in, we'll say I squirt 2 in, okay? And those mean 2 minuses. So when I initially squirt this in, the reaction between hydroxide and protons is really fast. So this reacts with this and makes a water. So now it's a water, so let's just make it part of the water. And then a second one reacts with this and makes another water. So we're going to get rid of this. But look, there's 2 of these left over. The solution's become acidic. That's why you see the initial flash of red. But then we got all of this magnesium hydroxide left over that slowly dissolves, just a little bit. So a little bit of this starts to dissolve. So if 1 more of these dissolves, I get another magnesium and 2 hydroxides. Oh, and it reacts with this, and this, and this, and this. And here the solution would be neutral at this point. So the color change would go from red all through the other colors to green at this point. And then when a little bit more is still left over, when a little bit more of this dissolves, we have some hydroxide left over, happens slowly. Bringing us back to purple again. But some of the solids dissolved, so we don't have as much as we did before. And this process can happen over and over and over again until we run out of the magnesium hydroxide. When all the magnesium hydroxide has been neutralized and squirting in acid has nothing to react with, it should stay red. And instead of being cloudy, it'll no longer be able to be cloudy because all the solid is gone. It should go to clear. Let's see. Let's continue to add some acid. All right, I'm going to add 5 drops. 1, 2, 3, 4, 5. Give that a swirl. There's the red. And woo, right back through green. And then slowly we're going to get a little change of color, probably more to blue or aqua. But I'm just going to keep going to see if I can't get this to go all the way to a clear, transparent red. I don't know how much I'm going to have to add. That's so fun. Is that it? Did I react all of the magnesium hydroxide away? I believe I did. I believe I did. So this is the point where all the solid has been dissolved and the addition, the solid has been completely neutralized. And when I'm adding excess acid, of course, the excess acid is what's giving the red color, indicating that we have an acid here in the solution. Probably be a good idea for you to try to write the complete and net ionic equation for this particular reaction. And when you do so, let's make it a little easier on you here. Let's just assume that we are doing a reaction between the sulfuric acid portion that's dissolved and the magnesium hydroxide portion that's dissolved. That'll make the complete net ionic equation a bit easier for you. All right, let me write these for you. Let's see, I'm going to have 2H plus aqueous from the sulfuric acid. I'm going to have the sulfate ion. That's going to react with magnesium 2 plus, and I'm going to get 2 hydroxides. This and this are going to give me 2 waters. And I'm going to end up with dissolved magnesium sulfate. Let's write it like this. For the net ionic equation, we better just have protons going to water. For the net ionic equation for a neutralization reaction, these 2 H pluses, those end up in water, so I'm going to leave those alone. I have a dissolved sulfate here and here, going in and coming out. I have a dissolved magnesium going in and coming out, and of course the hydroxide ends up getting locked into water, and so the net ionic equation would be 2H plus 2 hydroxides goes to 2 waters. There's some problems in the PowerPoint slide. Slide number 16, that deals with neutralization reactions and the complete net ionic equation for those. You should probably work through those.